So good afternoon, everyone. So today I will give you some information about my area of research. I think last time we talked and everyone know me. My name is Ayman Elbaz. I am a professor and lecturer of bioengineering. And as we mentioned last or in the first lecture, we have many areas in bioengineering. We have bioinstrumentation and the biomedical devices. We have molecular engineering and drug delivery. We have artificial intelligence, big data, and the bioinformatics, and this was my area. We have modeling, simulation, and this will be Dr. Filipo's area, and he will give you today also an overview about his area. And we have biomechanics, rehab, and engineering. I think Gina will give you some information. Before we start, I just need to pay your attention. Everyone knows that we have, this is the current certificate and degree from bioengineering. We have Bachelor of Science, we have M.Eng, we have Master of Science, we have PhD. I just need to focus about the last one, which is called Certificate in Artificial Intelligence in Medicine. If you decide to do either MS or M.Eng, you can take these 5 classes, and it will be considered as a part of M.Eng and MS, and you can graduate with M.Eng and Certificate in Artificial Intelligence in Medicine, or MS with a Certificate in Artificial Intelligence in Medicine. So this, if you decide to make M.Eng and MS, this opportunity, you can graduate it with this certificate. And this is classes can start when you are a senior student. You can start to take up to 2 classes from this is certificate, and then when you become M.Eng, you can take that. So I will start to talk about my area. My area is called Big Data in Medicine, and when we start to talk about big data, this is what we will be our input. But when to start to work with big data, you have to find what is the source of the data. For sure, since our field is medicine, the first source of the data will be the hospital. Now, if this is research is still under clinical trial, maybe you need to get some information from some labs in the hospital, because this is still under research or clinical trial. So we can get data from university. Also, in the smart city, you can start to have some information about the pollution in the city, because this can help us in the decision or in the diagnosis. And besides this, we have demographic data. So this is usually the sources of the data in the big data system. That when we start to work with big data, this is the places that we can use to collect data. So from these sources, what big data we work on? We have imaging. In imaging, we have ultrasound, we have X-ray, we have MRI, we have MRA, we have fundus images, we have OCTA. We have a variety of medical imaging. This is called medical imaging. For clinical data, for sure, you have urine test, blood test. All this you can get it from clinical data. In addition to demographic data. Genome, for example, genome, we can have DNA, RNA, or SNPs. So this is also source of the data that we can use. Pathology, you can get the pathology report to see the cells and the interaction between the cells and different stains. Environment, you have the sensors that give you information about the pollution. So this is now, this is in order to work in this area. For example, right now we have data analysis. Now, will you do everything in the project? No. When you start to work in a system like this is to develop a technology related to the medicine using the big data, you are not the only one who will do everything. You will be part of the team. So this is how we start to make the team. Physicians, they start to tell you about the problem, what is the current challenge, what is the gap between technologies. So the physician will give me this information. Then in the team you must have some IT team. He will tell you how to get access the data, how you will store the data, because this is data, it is huge. So we can tell you how you access it and how we store it. Computational power, for sure you must have some computational power like supercomputer or computer with high-speed GPU to help you to analyze this data. Scientists who will help you to put the hypothesis, because now you started to do something. So what is the solid science that the engineer will use to develop their solution? And commercialization. Since we are working on technology, I have to work with some people who know how to give me some information about the market, how they commercialize this market. So usually we have some people who have master of business administration, our team, to help us to make the connection between us and the industry. Is this still must be exist in the same place? Yes or no? Yes, if it is in the same place, that's fine. If not, we can use cloud systems that we can put this data in a cloud system, and everyone from different places start from his own place, start to access data and put his input. So we can work in, this system can work in one place or one site or different site using the cloud system or cloud storage. Cloud storage, we have now Amazon and we have Microsoft. Sometimes we can buy space in Amazon or Microsoft to put our data and we can access. Also, the Speed School here has supercomputer or cloud system. We use it in medical applications, so you can access it, but it's not the same size like Amazon or Microsoft. In my lab, this is the project that, or sample of the project. If you are interested in the brain, we are working in autism, we have dyslexia, Alzheimer, and brain cancer. If you are interested in the heart, we are working heart failure. If you are interested in the lung, we are working in COVID-19 and lung cancer. If you are interested in prostate and the bladder, we have project in prostate cancer and one in the bladder cancer. In kidney, we have acute renal rejection and the kidney cancer. Spinal cord center, we have project with Dr. Susan Harkema for spinal cord injury. For retina, we have two projects, one DR, for diabetic, and the second one for AMD. So today I just start with lung to tell you just some information about lung. Here, when I started here as a student in 2001, this was my PhD dissertation. I met with some doctor here in Jewish Hospital, they are radiologists, and this is how the physician started to tell me what is the gap in the technology, what is the current challenge. He told me this is the anatomy or the vascular system for the lung. So if the tumor exists very close to large airways, now this is called accessible tumor. You can reach it by biopsy, and you can take a sample and you can send it to the lab, you will notice malignant or benign. But if this tumor is far away from large airways, it is very difficult to access. So at this time, what is the current technology? They can tell the patient, okay, we have a nodules, you will keep follow up with us for 2 years. If it has become double in size, this is indication it is a malignant tumor. If it is still the same, it is benign. Okay, this was the current technology. The main problem is when you just tell the patient that you have nodules and you have to stay 2 years to tell you at the end what will be the final decision, this is puts the patient under stress. Especially more than 95% of the nodules are benign. So this means that it is most probably it will be benign, but you put the patient under stress to tell him this is answer after 2 years. Based on this is we started to talk with Dr. Folk, and again this is some statistics that the people who work with us in commercialization give us about lung cancer, how it is a big problem in US, especially in the state of Kentucky. The state of Kentucky considered #1 in US for lung cancer, and the percentage in women and the percentage in men. So this is some statistics about it. So the doctor told me if we can shrink, this is 2 years to 1 year or 6 months or 1 month or 1 day, it's much better. So this is the current challenge. We started here to use CT to make some analysis to to the lung tumor. This is how I started. When I started with imaging only. And so this is the imaging only. We take the tumor, we take the CT, we start to analyze the appearance. Because, and this is how we start, and this is very, very important. When you start to work, you have to talk with the doctor. How you know this is, when you look to the tumor, how malignant tumor different than benign tumor. He say malignant tumor, usually if you look to it, it is not homogeneous. Because usually the growth rate of malignant tumor is fast. When it is fast, the tissue will not be homogeneous. But the benign tumor, usually the growth rate theoretically speaking is zero or very little. So you will find it is homogeneous. So this is one feature, what's called appearance analysis. Since it is grow so fast, if you look to the boundary of the tumor, you will find the boundary of the tumor is not smooth. But benign tumor, since there is no growth rate or growth rate is very little, you will find that it has a smooth boundary. This is called shape or surface analysis. We started to do this, and I measured, this is what I did when I started my PhD dissertation. We started to take two CT scan, one today, one after 6 months to measure the growth rate. Then we make shape analysis, we make what is called appearance analysis, and we make the decision. This is give us accuracy around 92 or 91%. But now, and at this time, the advantage, I will go from 2 years to 6 months period. It was nice. Then we have here Jessica Sharon make a connection between us and Johnson & Johnson. Johnson & Johnson liked the idea, but they said we need to decrease the 6 months to be 1 day. In one visit, we can get indication if it is malignant or benign. In this case, I removed the growth rate. I just use shape and appearance, but I use another component, which making a breath analysis. The patient come and we ask him to take a deep breath, and we get the air, and we start to analyze this air. We have a chemical engineer. He developed this chip, and we measure 27 compounds, all of them related to carbons in the air. And we use this instead of the growth rate. And we develop this as artificial intelligence medicine to integrate the breath marker with the imaging markers, and we got around accuracy more than 96%. And this was a PhD dissertation of one of my students. His name is Ahmed Shafi. He just graduated last spring, and his dissertation selected the best dissertation at this semester. So this was one idea. After we do this, second step is, if it is malignant, the patient will go to chemotherapy. So now, when we meet the people from oncology department, they told us the main challenge like this, they start the chemotherapy, but they didn't know when they have to stop the chemotherapy. And this is very critical decision, because if they keep doing the chemotherapy, the patient will die from chemotherapy, not from the cancer. So this is one of the questions. So what we did here, we did now this time 4-dimension CT images. 4-dimension to capture the motion of the lung, like this. And from this dimension, we started to measure how elastic the lung. And now what we did after 3 or 4 sessions of chemotherapy, we make 4D CT scan. And we measure the strain, which tell me how elastic the lung. And based on this, we develop the technology to tell him, at this time you have to stop, because the lung, you will start to have what's called lung injury. Lung injury is that the lung it will lose its elasticity. This is how it is stopped. And this is what we did with Department of Oncology. And this is example of the team that I told you. We have engineer here, we have Jessica Sharon, her business, we have the medical doctor, we have the chemical engineer who told us, and we have here, this is radiologist, and we have, this is Dr. Van Berkel, he's a surgeon, because I have to get all the information or the feedback from all side. And also Dr. Falk is a radiologist, so we have in this team oncologist, radiologist, and surgeon. So this is very, very important. And when we go in front of funding committee, we like that the medical doctors start to talk, because they will tell them about the problem and they tell them what is the challenge, and if we develop this technology, how it will affect the survival rate. So this is very, very important. Then the engineer will come and they start to provide the solution. This is also the same idea. When we start, since we are working with the lung, we started to use the same idea for COVID-19. When the COVID came, we started to talk with the people from infectious disease, and they told us to make the diagnosis for the lung, you can make it by a rapid test or PCR. But what is the current challenge is prediction of the severity. Is this will be severe COVID or mild or moderate? Because if we know if this is severe, we can start early the treatment and we start to put this as biomechanical ventilator, because you know that severe COVID, it will need hospitalization and maybe need some support like mechanical ventilator. If it is mild or moderate, we will, again, we can tell him this is fine, you can return back to home, everything will be fine. And this is for stressing, one for cardiac, one for, first for the lung, we can have severe infection for the lung, or mild or moderate. For the heart, the same, it can mild or moderate or severe. And also we did it for the smell. We use it for olfactory bulb to see if the patient will lose his smell for 1 day or 1 month or 6 months. And based on this, we start to develop this system that we take CT, and for heart we use MRI or echo, and for anosmia we use MRI. And we start to make this analysis and we start to make the prediction, and based on the prediction, even we use this and the ultimate goal of this project to give this is prediction to tell the insurance company what will be the follow-up. If this is, for example, has severe chest, we can tell him he must follow up every 1 month or 2 months with the chest doctor. If this is severe in the heart, he must follow after 1 or 2 months with a cardiologist. But if it is mild or moderate, we can recommend this follow-up after 6 months or 1 year. So this is the main purpose of this project. And also this is a team that they are working in this project. What is the time now? I see you. You want to start? I can stop here.
Time is it?
It is 4:27.
How much more do you have?
I can just give 2 minutes or 3 minutes and you can do. This is project also, we did it here with spinal cord injury, and I love this project because really you will start to see how the science help the patient and improve the health care. So this is project we started to work with Dr. Susan Hakima in 2011. And the main idea here, and we have my student Samine is one which started to work on this project. And as you see here, the people have spinal cord injury. They can't walk anymore, and sometimes they have a problem even to control their bladder. So they can't move, they can't stand, even they can't control their bladder. So in this or bowel. So in this case, if they can't charge or discharge, it has a problem for it. So what we did here, Dr. Susan Harkema started to make a device, and this device that the neurosurgeon will connect to the spinal cord. And this device has 21 terminals. Each terminal can take from -5 volt to +5. In addition to the frequency, we can put 1 hertz frequency or 2 hertz or 3 hertz or 5 hertz. So we have this is variable, the voltage level and the frequency. This is our variable. Some patient can work with 0 and 5. Some patient work from -1 to 4. Some patient work from -2 and 1. So the lower level and the upper level is different. This one thing. Second, the frequency. Third, the combination. the combination that make me stand different than, for example, Hisham, different than Dr. Frios. So we need to find the combination, the frequency, and the voltage level. When we send this, Dr. Harkema, for example, if you need to stand, she know which muscles or which combination of the muscle, it will help you to stand. When the muscle contracts, it can take color from blue to red. Red means strong contraction, and this is what we are looking for. Because strong contraction, it will be like stable standing. Strong contraction, it will be stable walking. But if it is orange or something, this is mean unstable standing or unstable walking, so the patient can fall. So what we did here in this project, we start with the patient, during the lab, they try some combination, and in the screen, I will show the response of the muscle. If it is red, this is what I show here. This is the muscle, this is the signal that we got from the muscle, and this is how we display. When it is display red, they mean they able to capture a strong contraction. And this is helps Dr. Susan Hakima to speed up the training. And this is some example of the patient after we did it. I will put it here. See this? So there is no sound. But this example, after we started to turn on the device, this is the remote control that here. After you turn it on, you will find the patient will start. This is a device, and then we have remote control outside. Yes. When he pushes like this, he starts to able to move his leg. But the time he turns off the device, he will lose the motion. So the latest step of this project, because even we help this patient to stand and to walk, their movement is very, very limited. What this means? There is a chance that they will lose their muscle, and this muscle convert to fat. So what we did in this project, and also this is what Samini did, and Dr. Magdi participated in this project, is that we can try with every like 3 or 6 months, we measure the ratio between muscles to fat. And when we measure this ratio, we'll see if it is still the same or start to change. If still the same, this means the physical therapy course that they are taking is fine. But if they start to change, we can tell the physical therapy or the physiotherapy that they have either to increase the time of the course or try to use different type of protocols. Because if we lose the muscles here, what we did in the first step, it will not become useless. Because without muscles, the patient will not be able to stand, the patient will not be able to walk, and so on. So this is part 2. Part 3 of this project, since this idea is work, we started to use it for bladder. The same idea, but this time we will make the try to find the combination that makes the bladder relax. Once the bladder relax, it starts to fill with the urine. And when it is filled, we have a sensor to tell him it is filled. He will go to his restroom, and when he go to restroom, he will push the button that make contraction. And we started to work with this. Dr. Khalifa is working, Khalifa and Ahmed Nagla from my lab work with this project. But so far, we apply this in mice. We didn't apply this idea yet in human. And this is our team who working on this project. And I think now we have to stop, and Dr. Friebus will start to tell you some a short overview about his field.
So now I was told that you all already watched the slides, is that right?
Yeah.
So you already watched my slides, right? Good, then we just talk. So, okay, so the idea is that we apply math and physics and computation to try to understand diseases and try to then link this back to how the patients will respond to treatment. So in many ways, it is related, of course, to Dr. Abbas's research in his lab. But on the other hand, of course, it's a different angle to look at it. And so what we're doing is we're trying to simulate and model these diseases from the kind of the ground up, and to be able to get biological insight into this from that. So you all have picked engineering, in particular bioengineering, as your major, right? So any reasons why you picked bioengineering? I'm just curious. Yeah.
I want to do genetic editing, and bioengineering will allow me to do that.
Okay, and the purpose, the goal is ultimately what?
Well, the purpose for me is that I want to make agriculture better, more sustainable, and to have more produce than before without the need of pesticides and stuff like that.
Great, very good. Okay, who else?
I like biology.
You like biology? So, but you are a bioengineer, not a biologist. So why is that?
I'm good at math.
So no offense to the biologists. Right, okay. What else? Yeah.
I know a lot of us, like myself, are on the pre-medical track. And just having a background in engineering, specifically bioengineering, I feel is very helpful and perhaps important to being a doctor.
Okay. And do you know in what way? Do you have any idea in what way, perhaps?
Just like the mindset and like the ability to problem solve, and also I would like to understand the technology I might end up using, and just.
Okay, very good, very good. Yeah.
I want to make and develop prosthetics, and bioengineering seems like the best combination of electronics and the human body.
Very good, yeah. Okay, who else? Anybody else want to share while you're sitting in this room? Yeah.
I got interested because of tissue engineering, when I make artificial organs, artificial blood.
Okay, very good. Very good. So yeah, so what drove you all to this room and to this major is because you have the idea that you can do more than a biologist could, or perhaps some other type of engineering. And ultimately, as bioengineering, to help humankind in some way, benefiting humankind, either from disease or maybe from agriculture or some other way. So that's very good. So do you know what do engineers study? What is actually their object of study? If somebody were to ask you, what do engineers study? So for example, if you say, well, what does a painter deal with? A painter deals with paint. So what do engineers deal with? What is it?
Physics.
Physics? Okay, so physics is kind of a field, but
Systems?
systems, yeah, exactly. Engineers deal with systems, yeah. And how do we, so a painter uses a brush with his paint. What do we use to study systems?
Depends.
Math, technology, what else would it?
I mean, it depends what are we doing. Like, we can use photons and see, like, X-rays, for example, but there are different ways to get data and make things.
Okay, so analyzing data, yeah. So that's right, that's right. So engineers study systems and they use math, computation, physics to do that. And so as engineers, we have to study math. We have to study physics, and that's why you are taking and will take several more math and physics classes. And including also perhaps programming and computation, because those are our tools, those are our brushes with which we apply our paint, quote unquote paint, as engineers. That's right. And so it's actually very admirable, very noble of you to pursue this for the sake of helping humankind in some way as bioengineers. So for example, civil engineers will apply math and physics and computation to study structures. But we study living organisms. So what's the difference between a bio/living thing versus a structure or something that's inert, like a table?
It's more unpredictable.
It's more unpredictable?
Yes.
Okay. Why is that?
Complex.
What's that?
More complex.
More complex, and why is that?
A building doesn't grow.
Yeah, okay, so what is it about the biosystems that makes them grow and be unpredictable? What is it about?
Change. Cell multiplication.
What's that?
It's alive.
It's alive, that's right. That's it. Yes, biosystems are alive. And so we can never forget that as bioengineers. You know, I deal with structures, they're not alive. So if I kick this chair, it's not going to kick me back. But if I do something to a cell or to an organ, or actually to a person, they might punch me back, right? Yeah, exactly. So when we develop systems and technologies to study diseases and help doctors and other clinicians to treat patients better, or whatever we're doing with the environment, whatever, we have to keep that in mind, that we're dealing with living systems. And when we forget that, it can lead to massive failure in the work, that it's not going to succeed. And I can tell you many stories about that, but especially for the moment, I'll just mention in the field of cancer, which is my area of research. This is probably one of the reasons why cancer is still not cured, because we have forgotten that cells are alive. And so when we devise systems and ways to study them and to, in the case of cancer, to try to cure people, we have to remember that these systems are alive. So we use math and physics and computation to simulate this. We obtain data from clinicians, from experiments, from biologists. So some of the experiments we can do ourselves, some of them we do in collaboration with others. And then we integrate this to analyze the system as a whole. We apply math and physics and computation to understand it, to predict what it's going to do in the future. If I poke it this way, how is it going to respond? If I do this, how is it going to respond? And so there's many ways to do this, many ways to customize this. We use different things. We use in vitro experiments, where we do experiments with cells in the lab. We can grow little tumors in the dish, and you've seen that in the video. I think I have that in the video. We can analyze even finer detailed data, such as the metabolome of cells, and see how the metabolome affects how the cancer behaves. And we also get data from the patients themselves, through the doctors. We can get information about their history, what they're doing, what other diseases they might have, if they're smoking or not, if they're diabetic. So all kinds of things like this. And then analyze it and model and simulate what we think the response will be for the treatment. So I'm always open to having students help in the lab, but you know, it's a steep learning curve, and as I said, it requires math and computation, it requires commitment and perseverance. But on the other hand, I've had, you know, if you persist in that and are you know, kind of disciplined, the rewards are very great. I've had students be co-authors of publications, going to conferences, and of course some of them going on to medical school and learning about with collaborators. And then everything you learn doing the research, whether it's myself or any other faculty in the department, will actually help you with your classes, because it's kind of a yin-yang thing. You'll learn more about math and this and that in the research than you're actually applying this in your classes. You'll learn more with the classes you apply in your research. So it's always, and also in terms of time management and how you are motivated with your studies, especially in your major here. So if anybody's interested, you know, we can start on that. We can do a, you know, start some training and all this. And I've had students, that's how everybody starts somewhere at some point. And you know how to contact me, of course. So are there any questions?
Tell them what is your lab. Because your lab in downtown.
Yes, yes, I have a, yes, my lab is downtown. Yes, downtown Chicago. I'm kidding, downtown Little.
Because some of our faculties their lab here in Lutz Hall or Shoemaker, some of them their lab in downtown. So Dr. Philippus is lab in downtown. And what building I think?
Baxter too. Yeah. But you know how they can contact me. Yeah. So yeah, any questions about anything that I've said or anything in general about bioengineering or anything about anything? Yes.
You said you did cancer research. What sort of, I guess, specific aspects of that? Like, are you studying or do you have people doing in your labs right now? Like, what exactly are they measuring or what exactly are they?
Sure, very good question. So with lung cancer, we're actually getting specimens from patients when they are diagnosed with it. So it's like these are needle core biopsies that are very small. And we're able to analyze that for the metabolites and try to predict how they will respond to chemotherapy. Yeah. Yeah. And yeah. So that's one example. Yeah. But we have other projects. We have applied nanotherapy, for example. At some point, we're also developing nanoparticles to try to treat things better because nanoparticles can have less side effects and be more focused, delivering the drug, the treatment to the tumors. We have also looked at immunotherapy, trying to turn on the immune system to attack the cancer because right now tumors turn off the immune system so they don't get attacked. Yeah.
How many different projects would you say you guys are working on at once?
Actually, I have no idea. Nobody. No, I'm kidding. Well, we have several projects, some of them in different stages. So I would say there's probably about at least a dozen different projects. And so if you're motivated and you really want to pursue this kind of work and learn more about research and of course the goal is to contribute to this work, there's always more work than there's hands that can do it. Yeah. I tell the students there's like 10 trucks waiting outside to offload, and there's not enough hands to offload the trucks, or the tracks. This is your chance. Yeah.
Are there any particular aspects to cancer that are, I guess, particularly hard to simulate or predict?
Yes, the whole thing actually.
It's a false DNA.
That doesn't make sense, yeah.
Because we don't understand how something is alive in the first place. There's never been like otherwise we can't create cells ourselves. We can't create life, right? And cancer is actually a distorted way of life. So it's like another step beyond. Yeah. It's not just trying to understand something, it's trying to understand there's something being messed up.
Right.
Yeah.
Okay.
Yeah.
When dealing with people kind of outside of your field, what do you find is the most common misconception about cancer that you come across?
Very good question. Yeah. Any other questions? I'm just kidding. Unfortunately, that many times they think that it can be cured. And I can understand that because you don't want to have patients be hopeless. So there's always hope. And you always have the hope that this one person will be the one that's going to beat the odds and survive. And there's some who do that. And especially in the early stages, if it's detected early, the person probably will survive and may be okay for the rest of their life. But many times it's not detected early, it's detected late because it's asymptomatic. And then it's pretty much, I mean, they don't say this to the patient, but it's not curable. they'll just be able to live, but they'll end up dying from it, in spite of the treatments. Which is what has spurred me on to this research, because I think part of the problem is that a lot of the research with cancer has been driven by just biology, looking at things, and you're probably too young to know this, but 22 years ago when the human genome was decoded, it was touted as being, this is not going to cure all diseases. But that's nonsense, because most diseases are not caused by the genome. So here we are 22 years later, and of course, cancer hasn't been cured in decades. It's not yet.
Essentially, we have a machine, our body, that we can work, but we can't understand at all.
Exactly. It's actually more complicated than a machine because it's alive.
Yeah.
It's alive, yeah.
Where can we read more about your current projects? For instance, I would like to read more about your researching the role of the immune system in cancer growth.
If you can look at my website, and also you can email me, and I'll give you even more resources. Yes. Yeah. So how many of you want to go to medical school? Okay, a few. How many of you want to go to industry? Just one person, okay. The only one who wants to go make money. Okay, how about, how many of you want to go into research? Okay. Any other things I missed, like management or something else? Politics? So, yeah. Yeah, I think how much time do I have? What time is it?
I think 5 minutes.
5 minutes, okay. I'll be over in 2 minutes, how's that? Okay. So if you think about what do biologists do? What's the job of biologists? Yeah, research, but what do they research? What's their end product? What's the end product of biology?
Just data.
Knowledge, information.
It's knowledge, it's information, it's description. Yeah, exactly. And biology has traditionally been a very descriptive science, but unfortunately, I think especially with cancer research in many, it's not that we could have done it any differently, but the clinical side has been driven by biology. And it's not enough, it's insufficient. So doctors are trained essentially to be high-skilled mechanics who have a list of procedures to follow. A patient comes in and be okay, I have to go through A to B, I have to give you this drug first. I don't know if it's going to work, but I have to give it to you first because that's what these 300 patients benefited from compared to the other two. I'm just, for example, actually I do have a drug here. And then, let's see what happens. So each patient becomes its own guinea pig. We can do better than that, right? That's what we're here for as engineers. We want to do better than that and say, wait a minute, don't give him this drug. It's not going to help. This other drug here, our analysis shows that it could be of more benefit to this particular person, right? So that's the goal. And, we're different in many ways from other types of engineering, including mechanical engineers who study mechanical structures, and it could be all kinds of machines and things. And like I said, civil engineers, electrical engineers that study circuits and other things. We are focused on things that are alive, and in a way we become a kind of a jack of all trades. We want to kind of be able to apply our engineering to look at living systems. And like I said, we use math, computation, physics, and other tools, but our end goal is always focused on the living systems. So thank you so much. I hope I have inspired you. And if you need more inspiration, you can contact me. Thank you.